Hello everyone, welcome back to Aerospace Lab 2, and I hope you have had a wonderful weekend and are still staying safe. Okay. Today's discussion will revolve around motion, specifically linear and curvilinear motion. We will talk about the theory of motion, which you have learned in your basic physics, I assume, and as well as dynamics course. This is this is the lecture for today, and for the next lecture we will discuss the motion lab, which is essentially focused on whatever theory you are going to learn today. This lab is the first lab in a group of dynamics and controls labs, and so we are going to have the motion lab, which is this lab today, and then the vibration lab for next week, and afterwards we will have the control lab. So we are still working on the control lab. It is definitely going to be two labs, one lab, two or three labs, the control labs in general. One lab is essentially going to be an experimental lab working with a device we have already developed in the lab ourselves, which essentially is a control for a fan, for a CPU fan, right? We have a flow meter, we have a CPU fan over there, and you change the speed, and the mechanism that you have has to adjust the speed of the fan so your flow meter is the same value. So that lab can either be just a visualization. So the visualization is already set. You may go there, you may play with it, you may change the transform functions and everything to see the effects of it. Or I may require you to do a lab report and do an analysis. So we are still working on that one. But and then the next lab that we have in mind for you guys is pitch angle control. And this is going to be a numerical lab. You have to use MATLAB or Simulink to do this. So here we will, the theory here, we will talk about a little bit of flight mechanics and the effects of wind gusts and everything, which you have seen in the flight and orbital mechanics. And yeah, so, but we are going to start with the motion lab, which is the lab that we are focusing on today. Okay. And of course, every lab we are going to have a theory, and we are going to see the lab procedure and talk about the lab procedure as well, and how to read the data, how to calculate the analysis. But the theory for today's lab is pretty straightforward. You have seen it many times. So I assume that today's lecture will be a very short lecture. We'll just go over the basics and the important stuff that you are pretty familiar with. Hopefully you are pretty familiar with at this point in your education. Okay, so let's talk about the review of the basics. To describe the motion of an object, we must first be able to tell its position, which is a function of time at a certain time, with respect to a certain frame of reference. Okay. So what we are talking about here essentially, then you first have to have a frame of reference. Let's say this is your frame of reference, and we have already seen the different frame of references and the fixed frame of reference, the moving frame of reference, and so on and so forth. Right? We have already seen those. You first have to have one of these, and then you have to know the position of a point or of a mass with respect to frame of reference at a certain time. Okay? And when the position changes, which means that your object is moving, the change in the position is known as the displacement, x of t. The word itself implies an object being displaced or moved. Okay. And we can find the displacement, which is a function of time, of course, as your position at a certain time minus the position at the initial time. Okay, which we will call P of t minus the initial position. Okay, again, to illustrate this a little better, let's have the frame of reference x, y, z. This is P t of 0 or P0. Same thing. Your object has moved to the second position, right? P of t, and these positions can be identified with two vectors, right? Displacement is essentially going to be a subtraction of these two vectors. Okay, note that the displacement has a direction as well as the magnitude, and the SI unit for displacement is meter, of course. So based on this first step, the most basic step, defining of the displacement, let's define the velocity and acceleration. So we define the velocity from displacement using the displacement, and it is defined as the first derivative of displacement with respect to time, and its units essentially are going to be meters per second. So velocity, the first derivative of displacement with respect to time, or dx versus dt. And from the velocity, we can actually find the acceleration. We can define the acceleration as the first derivative of velocity with respect to time. And then based on this first derivative, we can conclude that the acceleration can be defined as the second derivative of displacement with respect to time. Okay. Before moving on, we have to make sure that we know about the Newton's law of motions and how they are related to the displacement, acceleration, and velocity, and so on and so forth. There are three main Newton's laws of motion. The first law talks about the inertia, which states that every object will remain at rest or in uniform motion in a straight line, unless compelled to change its state by the action of an external force. And then we have the Newton's second law, which is the most important law in mechanical engineering and aerospace engineering in general. The second law explains how the velocity of an object changes when it is subjected to an external force. For an object with a constant mass m, the second law states that the force of S is the product of an object's mass and its acceleration. So your force is going to be m multiplied by a. And you always have to keep in mind that the summation of all forces is equal to m multiplied by a in each direction, of course. And the third law states that for every action or force in nature, there is an equal and opposite reaction. In other words, if an object A exert a force on an object B, then object B also exerts an equal force to object A. Okay? So based on these definitions and based on the second Newton's law, we can have another look at the acceleration, and we can define the acceleration by the second law. So we have, this is going to be your main equation based on the second law of Newton's second law. We can define the acceleration to be A equals to sigma F over m. We can actually have a closer look at your mass as well. So for larger masses, you will need a larger force to maintain the same level of acceleration. Give you an example. Let's say your m is 1 and you want to keep the acceleration to be 1. Your F must be 1 newtons. Of course, the units are different, but when your m is 2, to maintain the acceleration of 1 meters per square second, you have to have a force of 2 newtons applied to your object, whatever object it is. So essentially we can define mass, let me write it here. We can define mass as the resistance to linear acceleration, right? Which means that to maintain at the same level of acceleration, you have to have a larger force when dealing with a heavier object in general. Okay. So acceleration can be dynamic or constant, which means that it can be time dependent or constant. Dynamic or time-dependent acceleration is called instantaneous acceleration, mainly because it changes at each instant. Okay, let's do a quick summary. So far, we have introduced the kinematic quantities of motion. We have introduced the displacement, which was defined the difference between an initial position and a certain position after and the position after a certain time. And we have also defined velocity as the derivative of x with respect to time. We have defined acceleration, and you have to keep in mind that all of these are vectors, right? So you always have to use the vector notation. But so far as you have seen in many of the upper level courses, we use bold lettering to identify vectors. But when I'm writing, I cannot use bold lettering, so I'm just gonna use the vector sign. And we have also became familiar with the one of the important parameters in the kinematic quantity, in the motion analysis, essentially, which is time. So the very first definition is a time-dependent definition, right? The difference in the position of an object, the distance an object has traveled, essentially, after a certain amount of time, okay? So let's talk about the big four equations of motion again. Let's say, let's generalize our discussion and assume that you are starting with an initial velocity, okay? So we can find the distance based on your current velocity at a certain point, after a certain time, and the initial velocity, okay? So V naught is always going to be initial velocity, and V is the velocity at a certain time. T is of course time, and 1/2 is just a number there. So you can find the distance by having the time that has passed from your initial position and the velocity after that time and the initial velocity. So you may ask, what will happen if your initial position, if you don't put the frame of reference on the initial position? So here we are already assuming that we have put the frame of reference on the initial position, meaning that your P T0 is 0, 0, 0, x, y, z, and T0 as well, initial time, right? Essentially, if you don't do that, if your P0, P naught is not 0 and 0 and 0, it's x, y, and z, essentially have to add an x naught in your analysis, right? But for the most part, we assume that frame of reference is at x0, but to be to represent the most general part, you have to do the analysis. So essentially, this is delta x, right? Equation 1. Second equation relates the velocity to the acceleration and time. So your velocity after a certain time is your initial velocity plus the acceleration multiplied by time. And then we can actually, for acceleration, we can double integral the definition of acceleration, which we had here way back. The definition of acceleration, which we had here. We can double the integral this, okay, and get to the one of the most famous equations in motion, which is this, which relates to your the distance traveled after a certain time, your initial x naught, initial velocity multiplied by time, plus 1/2 a t squared. Okay, a is your acceleration and t naught, t squared is your time squared. And based on these, if we combine these equations and play with them, we can actually find this relationship as well. V squared is equals to V naught squared plus 2ax. Let's see how we can get to this equation. But the rest of it is pretty easy. It's either using the definition or taking the integral, right? But this one is a little trickier. You can actually get to this equation using the first three. I'm going to use this, the second equation. put the two sides to the power 2. Okay, so you're gonna have v squared is equals to v naught squared plus a squared t squared plus 2 v naught at. Okay, and then we simplify this part. We are going to take the two a out. Okay, so you're gonna get 1/2 at plus v naught t, which is this is x minus x0 from the third equation, right? And we are assuming that x naught is 0. So you are gonna get to this equation. V squared is gonna be equals to v naught squared plus 2ax. Okay, so using these equations, you can actually find the displacement, the velocity, and the acceleration. We can also measure all of these using an experimental apparatus, right? Or using a device. And we're going to get familiar with the device parts of these measurements in the next lecture and also in the lab. We can have a similar analysis for a rotational motion. So far we have talked about a linear motion, right? Well, what if something is rotating on an axis? Okay. So when all the particles of a rigid body move along paths which are equidistant from a fixed plane, the body is said to undergo planar motion. Okay. And in kinematics, we studied motion along a straight line and introduced such concepts as displacement, velocity, and also acceleration. This is translational motion, which can be rectilinear and curvilinear. But the motion, as I mentioned, can be about a fixed axis for all the particles in the rigid body. And this kind of motion is called a rotational motion. Motion can be general too, so essentially a combination of translational and rotational. We are not going to talk about the vibrational motion in this lecture, but that's a discussion for another lecture. Okay, so different types of motion. We are going to have the rectilinear motion, we are going to have the curvilinear motion, and we can have the rotation about a fixed axis. So these two motions are the motions we essentially just talked about, rectilinear and curvilinear, right? Or the translational motion. And this is the rotation about a fixed axis, is the motion we are going to talk about now, right? And we can also have a combination of the two, which is a general plane motion, right? So we can have some sort of a rotation about a fixed axis, and your object can move along a path as well. Well, how can we define the rotational motion? let's take a look at this circle here. We have a center of the circle or center of the coordinate system O and the diameter R, and the idea is this disk is rotating along its axis. So after some time, the angle is gonna make with your horizon or your initial location of each point. Let's say initially this point that I'm drawing here, is located at this location. So this is going to be your initial location, your initial angle, or your horizon, whatever. And after some time t, it essentially moves along this path S, and the angle changes to t. And we want to find the equation that relates all of these parameters, right? So the rotation angle, theta, is the amount of rotation at a given amount of time, at a certain time, and is analogous to linear displacement. So we have rotation angle, which is analogous to linear displacement. Okay, so it is called, because of this analogy, it is called the angular displacement theta. The angular displacement can also be defined as the ratio of the arc length, which is this length, the rotational motion has experienced, so the past this point has moved on this disk, okay, to the radius of the curvature with respect to the rotational axis, which is this axis here. So we can find the rotational angle or the angular displacement at this path as this arc length divided by r, okay. We can also define an angular velocity omega, which is the first derivative of your angular displacement theta with respect to time, which is first derivative, right? And we can also have an angular acceleration alpha, which is the first derivative of your angular velocity with respect to time, and the second derivative of your angular displacement with respect to time. And based on this, we can actually take the integrals and find those general equations that we did for the linear motion, for the translational motion, essentially curvilinear and rectilinear motions, right? And get to the equation 3 from those motions as well. So your angular displacement is going to be initial angular displacement plus your initial angular velocity multiplied by the time that has passed, plus 1/2 multiplied by your angular acceleration multiplied by time squared. Okay, we can actually have all of the equations we had for those motions for the angular motion as well. But let's see if we can find a relationship between the linear analysis that we have had for a certain point P that we have been using so far on this disk, because as far as this P is concerned, the P itself is moving, point P is moving a curvilinear along a curvilinear path. So we should be able to define displacement, a linear displacement, as well as a linear velocity, linear acceleration, and all of those things. And you always have to keep in mind that whenever we are talking about acceleration in these lectures, we are talking about the tangential acceleration. If we are talking about the acceleration of a point P on a disk or a ring or whatever, it is the tangential acceleration, right? So to find this, the path, the displacement, the linear displacement, we essentially have to find the arc length, and we already have an equation that help us find the arc length, right? That's your curvature radius multiplied by theta, angular displacement. We can define the velocity, and this is the linear velocity, as ds versus dt. So the first derivative of the path with respect to time, and then we can replace s with r theta here, right? R doesn't change. That's the first assumption. So we can take it out, and that doesn't change with respect to time. All right. So we're going to have r d theta with respect to time, which is equals to r omega. You can have the same analysis for the tangential acceleration. It will be the first derivative of your velocity, your linear velocity with respect to time, which is going to be equal to r, your curvature radius, multiplied by your angular acceleration. Okay. So far we know everything about the simple linear motion and a rotational motion. We know the relationships between the two. But here we want to find, the next step is to find the analogous law in the rotational motion, which has an analogy to the Newton's second law. So the rotational Newton's second law, if you will. So, to do so, we have to define the moment of inertia, right? Which is I, which is defined as I. And using that, we are going to talk about the moment of inertia and a little more. But then using the moment of inertia and the angular acceleration, we can actually have the Newton's second law for a rotational motion. So that's going to be applied to moments, right? Instead of forces, because we are in a rotational motion. So the combination of all moments, the summation of all moments, is going to be equals to your moment of inertia multiplied by your angular velocity. Again, I is the moment of inertia, and this moment of inertia, we said this about the mass, right? Mass was the resistance of the body to the linear acceleration, right? But I, which is the moment of inertia, is a measure of the resistance of the body to angular acceleration. And again, it is analogous to the translational motion, where mass is a measure of the body's resistance to linear acceleration. Okay, so let's define this moment of inertia mathematically for a general body. Let's say you have this general body and it's rotating around this axis, right? Your moment of inertia is going to be the integral of second moment about an axis of all the elements of mass dm. So what does it mean mathematically? It means that your integral of r squared dm, right? And m is your density multiplied by your volume. So we can replace that. Density doesn't change in our analysis, right? So we're going to have a volume integral of r squared rho dv. We can take rho outside of the integral and have the rho in a volume integral of r squared dv. Okay, this is going to be the definition of the moment of inertia. And let's talk about two theorems that relate to moment of inertia and the analysis of the moment of inertia. You always have to keep in mind that the moment of inertia is defined in two different directions, right? In three different directions. So it is a directional parameter, right? The first theorem we want to talk about is going to be the perpendicular axis theorem, right? This theorem is only applicable to the planar bodies. What are planar bodies? Planar bodies are the bodies which are flat with very small or negligible thickness. So essentially two-dimensional bodies, right? So for this type of body, let's say you are talking about a disk which has a very large radius and a very small thickness, so you can essentially assume that thickness is negligible. And the moment of inertia in the z direction, which is the axis perpendicular to that plane, the plane of the body essentially, is going to be equal to the moment inertia in the x direction plus the moment of inertia in the y direction. Okay. The second theorem that we want to talk about, and this is the last thing we want to discuss in this class, and as far as the theory goes, is the parallel axis theorem of moment of inertia. Parallel axis theorem is applicable to bodies of any shape, and it states that the moment of inertia of a body about an axis parallel to an axis passing through the center of mass. Okay, so we are talking about the two axes here, two different axes, right? One of these axes is parallel to an axis passing through the center of mass, okay, is equal to the sum of the moment of inertia of the body about an axis passing through the center of mass and the product of center of mass and the square of the distance between the two axes. So this definition may be a little confusing, but let's try to make it a little clear. Let's say you are dealing with this type of body and you want to find the moment of inertia around A, the axis A, around all axes that pass through A, right? Of course, you can have axes that are parallel to the center of gravity or center of mass in this case, right? Right? To find the moment of inertia of this body with respect to this axis, we essentially have to find the moment of inertia with respect to the center of mass, right? And then find the distance between the center of gravity and the new center of coordinate system, if you will, which is going to be the distance d. Okay, and this d can have x, y, and z component. So you have to keep that in mind. And this is a general definition. And then multiply that by the mass of the body. Take it to the power 2, multiply it by the mass of the body, and add the moment of inertia around the center of gravity to it. So this will give you the moment of inertia around the new frame of reference, if you will. Okay. So as mentioned, this is the last slide about the theory of this lab, and this is not the last slide. Sorry. So the final summary essentially is that in the lab we are going to measure the motions. We are going to be focused on measuring the motion and its component, velocity and acceleration. We can of course get from displacement to acceleration directly using this equation and this equation, and this is going to be your setup for the lab 3, which we will discuss in detail in the next lecture. Okay, so that's it for today, and have a good day.